In this video we cover similarity and convolution. Why are these two topics related? That is for a very simple reason. Similarity, not just in computer systems, but as it appears also in the human sphere, in the biological sphere, is very often implemented as a form of convolution. So what are we going to do? We are going to browse briefly to what convolution actually means. But first we give a motivation. What is similarity? How can human beings perceive two artifacts or two abstract entities as similar? And once we've established that, we will go through a number of features on the side of the notion of similarity and convolution. Okay, one thing or one major starting point for the investigation of convolution was the work of Plato 2,500 years ago. He already distinguished some stimulus from the actual reality behind it. So he would say that what I perceive is just an image of what is actually happening. There is, for example, the analogy of the cave, which we are not going to do now, but two very important terms that he used in order to distinguish the image from the actual reality are the icon, the eikos, and the eidos, the icon. Okay, so what did he mean by that? By that he meant two relationships. In order to be related by the eidos, the image and the reality, or actually two real artifacts, must be related by properties. For example, they must share certain features that are nameable, that can be expressed in some form. To give a very simple example, what combines a human being with all sorts of animals, in particular mammals, is that they are alive, that they are able to move around, that they give live birth, and many other things. Each of these properties is actually a predicate of their existence. Predicate means that something is either present or not present. So the eidos refers to predicates and their presence or absence. Okay. A relationship by the icons sorry for messing this up, is an overall thematic similarity, as it is also called. That means if two people look similar, for example, father and son, mother and daughter, if they have a similar face, then they are related by the icons, by the overall, or as I said, by the theme, by the thematic. Yeah. That is also a very important relationship. So, that is what Plato said. That was investigated on the philosophical level, discussed for centuries, and the real psychological, quantitative research in that area of similarity measurement only started much later, in particular in the 1930s and later on in the 1950s. One of the pioneering works was by Goldmeier, who investigated geometrical primitives, triangles, rectangles, squares, and tried to identify by what properties, by what predicates, and by what themes they appear to be similar to human beings. And what Goldmeier found out was that there are basically two types of similarities. One is integral. he said, and the other one is separable. If somebody is integral, then it cannot really be distinguished from the content of the, in his case, visual stimulus that was given. So he would give the students, for example, triads to choose from. Triad means that you have one reference and then two alternatives, and you must pick one of the alternatives as the one that is similar to the reference. So if these were these properties that he was investigating, like for example the overall shape, triangle versus square versus circle, then he would call that an integral property. One of the paramount integral properties was the size in his case, so something that could be measured on a quantitative scale. If it was a property that could actually be expressed in terms of absence or presence, so in predicates, he would call that a separable stimulus. And he would find that these two elementary forms of similarity are the two components by which the entire human similarity perception can be explained. That means similarity is integral stimuli plus separable stimuli. He would not consider, as far as I know, the ideas that were developed by Plato, but for us, of course, it's easy to map them. The thematic notion, and behind that the icons, is apparently related to the integral stimulus, whereas the eidos and the separable stimuli also express the same idea. By the way, predicates are measuring on scales that are called taxa. You might know the term from biological taxonomies. So what is behind that is very often a taxonomy. And therefore it's called also a taxonomic relationship, in contrast to a thematic relationship. Okay, so similarity research continued. There were valuable contributions, in particular in the 1960s, 70s, and up to the late 2000s, and it converted towards a point where researchers would actually say that, well, this notion of integral and separable is certainly what defines the ingredients, but it does not yet express how the individual measures similarity. That function was called a dual process model. One of the first is a very famous one. It was defined by Amos Tversky in the 1970s, of course, with co-authors, which was called the feature contrast model. The details are not very relevant here, but what he said is that there are actually stimuli components of the, for example, visual presentation of an image, a video, or it could also be something audible. It's just that the psychologists would prefer visual stimuli because the experiments could be done more easily, that are either absent or present, the predicates that we just had. These are called A, and then he said that this is contrasted by properties that are present in just one of two stimuli. So if I, in a triad, for example, compare a reference to one alternative and the other, then it's a pairwise comparison between the reference and the first alternative, and later on between the reference and the second alternative. And stimuli, or properties that are only present in one of these two cases, were denoted as B and C. If we sum them up and subtract them from the common properties, we have a contrast between what is common between the stimuli and what is different in the stimuli. And that was the first notion, without naming it actually, of a dual process model of similarity. Later it was defined in greater detail, and it was also found out that description of similarities can be done with one particular function very well. It was also identified that these differences can be expressed by another function, and there was also found a way how these things could actually be combined together. As we said, one is about similarities, the other one is about distances. Okay, let's have a look at the similarities first in the dual process model of similarity. The function that we usually use here, or that is the most extreme similarity measure, I once defined or actually collected a list of similarity measures and found with variants more than, I believe, 120 different ones that were here and there defined in the literature, in particular since the late 19th century. In the early stages, of course, without referring to the notion of similarity, but only saying that it makes sense to sum this and that up in this and that way. But it was a similarity measure, and in particular from the 1970s, 80s on, also with the conscious notion of that here we are dealing actually with similarity measurement, something deliberate, something imitating of human behavior. So when I did this and when I compared these measures, I found out that one measure is, so to say, the prototypical similarity measure, and that is called the convolution operator, which is, for example, used in deep neural networks and in many other types of machine classifiers, support vector machines, for example, radial basis functions, and many others more. The convolution pattern is the inner product from algebra. It is defined as if I have two stimuli, x and y, as their inner product. Yeah? Which can be defined, or which is defined as the sum of the product of the components. And this is normalized usually by the length of the vectors, but normalization in this respect is something for which we don't care very much here. So we have this building block. This is called convolution. So what might x and y be? X and y are, in our context, usually stimuli, visual stimuli, images, frames of a video, motion vectors between videos. Might also be some text, words, phrases, phonemes on the other end. Might be the notations of stocks on the stock market. Might be might be elements of music like overtone structures, rhythm patterns, and so on. So it might be a lot of things. It's very easy to think of them in the context of images. Then it's a patch or an entire image or a video frame. So if I compare two images by the inner product, it means that I compare them at every single location. I might be an indicator for something two-dimensional, three-dimensional, or how many ever dimensions you have. That doesn't matter so much. What it does is employs two functions. The two functions are multiplication. It means the elements are multiplied with each other. Later on, they are summed up. So what is the multiplication doing? It is doing something very important. It is giving a bonus to the two compared stimuli if in the same position they have the same value, if they square each other out. That gives us, multiplication is a geometrical operation, gives us the maximum square. That is, inherently in convolution is a similarity measure because it multiplies the individual components. Of course, normalized over some, oh sorry, it's not possible to see that, over some length of the individual vectors x and y, so they have a norm length of 1. But as I said, these are technicalities not so important here in order to understand what it is about. Okay, what is important is that applying a geometrical operation gives a bonus to high values, to similar values, and on the other hand, if one value is small or even 0, gives a large penalty to this product. That is the multiplication operation. These individual multiplications are then summed up over all locations. In the image, apparently x and y direction. In the video, additionally a time direction. In the audio, it's just one-dimensional, but it might be stereo, one-dimensional over time. So the individual values of the membrane, of the loudspeaker, or on the other hand, of the microphone. But two-dimensional in terms of overtones that you have that matter at the same time if you do a frequency analysis, and of course mono and stereo or how many other channels you have. So it doesn't depend on the dimensionality here. Convolution is a similarity measure because it multiplies the individuals, and those give a penalty for differences. Those give a bonus for similarities. That's why it's a similarity operation. Summing up is just natural because before that we took the individual vectors and divided them into their components. So we have to sum up on the other hand. That's just logical. This is a trivial operation, but this is what is behind the convolution operator. And it is important because this form, the inner product, is actually at the center of similarity measures. I compared this huge list of measures that I collected in a systematic way and found out that if you want to measure similarity for individual data types in different domains, then you will not find a more extreme and more discriminating similarity measure than this convolution pattern. It is one end of the scale of similarity versus difference or distance. Okay, having said that, let's look at the other end, which is this B plus C. So these are the properties that are only present in one of two stimuli, X and Y. Well, how is it defined? It can be defined in many ways. There are even more distance measures in the statistical literature, psychological, other social sciences, other technical sciences. There are hundreds of them, basically. One very famous family are the Minkowski distances of order P. And in this family, the simplest form, so to speak, yet one of the most popular is the city block distance. And the city block distance is defined as D is once again a sum over components for two vectors x and y. But this time we are not multiplying, so it's not a geometric operation, it's just an arithmetic operation. We are taking the difference between the individual components, and of those we are interested in the absolute value. The bigger, the more different. And summing up over the individual components means that the entire notion of difference, of distance, is actually based, sorry, it's giving in obviously, is actually based again on this minus alone, okay? This is where distance happens in the L1 norm. It's called the L1. L2 would be if I square these out. So if these are brackets and then we square it out, then of course we have to take the square root, also known as the Euclidean distance. Okay, this is not about Minkowski distances. It's just about comparing similarity with distance, with difference. And in my experiments, I found out that this pattern, the L1 norm, is the exact opposite of the convolution operation. It is the most extreme form of distance measurement you can have. You take the pure absolute value of the difference, unmitigated in any way, and therefore punishing every deviation in terms of similarity. Well, punishing here means, of course, that the value for the distance gets higher. This function, let's take this here, is, as I said, on the opposite end of the inner product. It is usually called just a distance function for the sake of making them comparable. I use the classic notion. I use the classic notion for the inner product. And on the other hand, I call this thing sometimes negative convolution. This, however, is just my own name, in order to make clear that the two concepts are actually highly related, the distance and the convolution. For example, you employ convolution, as I said, in most machine learners. It's just a natural thing to use there. Support vector machines, radial basis functions, and so on. On the other hand, you have negative convolution in many signal processing operations. For example, for predictive coding, linear predictive coding, you will always employ a distance function. In certain integral transformations, you will also rather employ a distance function than a similarity function. In others, just like the Fourier transformation, for example, you will have again the positive convolution pattern. So, in order to make the people aware that positive or negative, it's both an act of element-wise comparison and summing up over these elements. So it's in both cases a convolution operation actually, and inverse to each other. As I said, opposite points on a scale. I named this negative convolution. But as I said, it's only my name. So we have a solution for the common properties. We have a solution for the differences between two stimuli, X and Y, two images, two words, two sentences, two types of behavior, aggressive behavior versus sporty behavior, whatsoever. The question is now, how do we combine these two? And the pattern that is between those is usually referred to as the generalization function. The generalization function is a function that measures similarity given distance. Some nice color. Let's make it brown. Okay, so what do we do here? We have distance and we want to convert it into similarity. For a very long time, academics were happy and content with assuming that this is basically a Gaussian function. So E minus some function of mean, X, and standard deviation. Yeah? Okay, from the 1960s on and 1970s, there was a lot of serious research in that area, which came up in the event with a generalization function that looks like this. That was by Professor Shepard called the universal law of generalization, which is E minus D. Later on, this was again generalized into another function, which was defined by Professor Tenenbaum, which is still the pattern, right here, which is still the pattern of the universal law of generalization, but which adds a constant area in the beginning, or at the top, at maximum similarity. So that means if there is no distance between our two stimuli, whatever they are, words, images, and so on, if there is no distance between the two, then of course the similarity is at the maximum. Any distance that occurs would be punished in the red line in the universal law of similarity of generalization, immediately. Tenenbaum now argued that in practice this is not the case. We as human beings are ready to accept a small deviation and still consider the similarity at the maximum between two stimuli. And therefore he introduced this span with a constant maximum similarity. However, if you look at it, what we have in the end is very similar to what we had in the beginning of the discussion. And since this is about human behavior, about psychological, sociological, or let's say human studies, so it's never fully precise, and the differences between the individuals are rather bigger than the commonalities of the individuals, then of course these differences have to be considered as very small. So quite probably the original function, which was used until the end of the Second World War, was to a degree fair enough. Okay, so to sum up this picture that we were painting here is similarity is a function of two components. It is about something that is separable, where I can argue and say, well, this is based on some taxonomy. I have to have certain properties present. If these are present, I can compare them. And those that I compared, I can actually count. And if 10 common properties are present, then I say two things are similar, two stimuli. So this is a high-level cognitive process, apparently. On the other hand, we have this integral notion where we cannot really express or often what actually the similarity is. It's an overall theme. It's something that makes them look similar. An outline, for example, a shape, a size can be similar also. But it's still there and it still gives you the impression. So where this is on a high cognitive level, the other end, the integral stimuli, is on a lower, more, if you want, emotional level. Though it's not about emotions here, actually. Okay, and both functions, both elements contribute to our notion of similarity. Okay, and this pattern can be expressed, the two types and their merging, by the act of convolution. And that means that we use the one function for convolution for the predicates, for the taxonomic part. We use the other end, the negative convolution, for the thematic aspects where we measure the distance, and we combine them by employing this function of generalization on the distance, thus converting distance into similarity and being able to assemble them into a dual process model, which in the simplest case is just summing them up actually, and by that being able to express. Now, where do individual differences between human beings come in? Mostly in the weighting of the taxonomic and the thematic part. Scientists have, for example, found out that there is a very small gender connotation. Females tend to use more taxonomic comparisons, where males use more thematic. However, this is a very, very small correlation. As far as I remember, the individual differences are much bigger than the gender aspect. So it's not something one should dwell on very much. In summary, convolution is at the heart of the way human beings perceive similarity. And that makes this function very, very interesting when we look into the neural part of processing, or the neural form of processing in the human brain, where we will see that the neuron is essentially the individual component, the individual building block is essentially a convolution operation, which is able to perform both similarity measurement and distance management. That comes in a new video, please refer to the e-learning platform for the outline and the sequence of the videos. Thank you.